Welcome. Thank you for joining Hydro International's webinar on understanding grit and evaluating grit removal technologies. My name is Marcia Sharoni. I'm the sales director for Hydro's division that covers water and wastewater applications in the Americas. I've been in the industry for about 35 years, working with market leaders in liquid solid separation. I've been at Hydro for the past 13 years. Much of the information I'll be presenting comes from a WEFTEC paper that Hydro co-authored with Hampton Roads Sanitation District. I may refer to them as we go through this as HRSD. The paper was called The Relative Performance of Grit Removal Devices. It was presented at WEFTEC in 2014. The performance data has been supplemented by other WEFTEC papers, information from industry design manuals, and Hydro's more than 50 years of experience using Vortex Flow to separate liquids and solids. The objectives of our presentation today is to encapsulate published data on the conventional approach to grit and why it has not protected plants from grit deposition and abrasive wear, the impact of poor or conventional grit management, grit removal objectives, and grit basics. We'll compare the performance of the most commonly used grit removal devices using a single consistent test methodology. By using the same test methodology, a comparison can be made of these common technologies. We'll also review the test method used and why it was found to be consistent, repeatable, and effective. Grit management historically has been undervalued and until recently, in many respects, ignored. Traditional design guidelines have not protected plants from abrasive wear or deposition, and ease of grit system operation has been more important than the removal efficiency. The current trend is to put a higher value on grit, similar to the trend in the industry has seen in screening over a last number of years. Conventional screens were often very coarse, maybe 3/4 inch, while today probably the standard of the industry is about 1/4 inch or 6 millimeter. The trend has also been driven by advances in treatment processes. Plants are getting smaller and achieve better effluent quality in a smaller footprint. The smaller footprint leaves no capacity to store grit. Advances in sludge processing and disposal options are less tolerant of both rags and grit. And plants are also operating with tighter budgets, meaning less staff and less funding to clean and repair equipment impacted by grit. But there are still challenges. There's no industry standard for sampling or characterization of grit, nor a standard performance or removal requirement. In addition, owners and engineers are forced to navigate a field of what can be conflicting performance claims made by various equipment manufacturers using differing test methods, which makes these claims difficult to verify. So let's start at the beginning with the basics. The conventional wisdom or design point for grit removal systems has been 210 micron particles and larger. And that design point also assumes that all grit are perfect spheres of silica sand, all 2.65 specific gravity. I traced this design point back to a 1942 paper written by Dr. Thomas Camp for Sewage Works Journal. The article was written when he was still a university professor and had not yet left academia to form Camp, Dresser, and McKee. Millennials, you may know the firm better as CDM. And no, this picture is not Dr. Camp, but it is representative of the era and the technology of the area to show how long ago this design standard was adopted. In 1942, treatment processes were much less advanced and needed less protection from grit as well as screenings. At the time, many plants only had primary treatment processes. Secondary treatment processes were just being implemented and were not yet mandated. In the paper, Dr. Camp states that experience, not data, indicates a 0.2 millimeter or 200 micron design point, and it generally removes grit, which gives trouble in treatment plants. And that paper set the design point that has remained virtually unchanged and unchallenged for over 65 years. That 60-plus-year-old design point does not protect plants from grit. These photos are not uncommon. Many plants deal with grit deposition in their aeration basins, primary clarifiers and digesters, and abrasive wear of mechanical equipment throughout the plant. So understanding grit is the first step in improving grit system design. Grit is assumed to be perfect spheres of silica sand, all 2.65 specific gravity. If you've ever been in a wastewater treatment plant, you know that wastewater grit is made up of a variety of materials, shapes, sizes, and specific gravities, and all of those factors impact the grit settling velocity. While grit is assumed to settle or behave like clean sand, it does not. A sphere of silica sand of one size can settle at the same rate as an angular or irregular shaped larger particle, which has a higher drag coefficient than a sphere. An even larger particle of irregular shape and perhaps a lighter specific gravity can also settle at the same rate. This makes grit settling velocity or grit behavior a key to an effective grit removal system. That's exactly what Hampton Road Sanitation District found. Hampton Road Sanitation District operates 13 wastewater treatment plants in Southeast Virginia. In 2007 and 2008, they started a journey to understand the effectiveness of their grit removal systems as they were planning an upgrade to their Army-based treatment plant. In the upgrade, they wanted to incorporate a grit removal technology that would protect the plant from abrasive wear, reduced operating volumes, and increased maintenance and repairs. That they had experienced these issues at several of the other plants. In 2007 and 2008, they evaluated 3 different technologies at 5 of their wastewater treatment plants. They also tested 2 additional technologies to evaluate for the Army-based treatment plant upgrade. Both of these papers were presented at WEFTEC in 2009. The method that they utilized a vertical slot sampler, which is a PVC pipe that's placed in the channel. The pipe has a slot cut to face upstream. Flow is pumped from the inside of the pipe, which allows a sample to be collected from the entire vertical water column. The bottom of the sampler or the pipe is closed to prevent drawing material that's deposited on the bottom of the channel into the sample. The slot width is a function of the stream velocity, channel depth, and the pump velocity. The slot width is sized so that the velocity into the pipe is the same as the channel velocity. This testing method has been used by many municipalities and engineering firms across North America for almost 20 years. The sample is then pumped to a continuous collector, which you see on the right, over a period of time, typically 4 to 6 hours, to account for variances in grit loading during diurnal flow variations. The collector is fed tangentially so as not to disturb and resuspend collected grit. It's fed into the collector at a rate that will maintain a low surface overflow rate on the collector, low enough to capture grit particles as fine as 50 micron. After the sampling period, the material is allowed to settle, then water is decanted from the sample, loose floatable organics are rinsed away, and the excess liquid is drained. The sample weight and volume are recorded. The sample is then poured over a stack of sieves to separate the material into size fractions. Wet sieving allows accurate sizing of the grit as it appears in wastewater. Drying the sample in a muffle furnace will burn off any attached organic material and can fracture particles. The material in each sieve is then processed in a modified Imhoff cone to determine the settling velocity of the different size fractions. The modified Imhoff cone is used to measure the speed at which each wet size fraction settles. Grit settling velocity is expressed as SES, or sand equivalent size, which is the clean sand particle size which settles at the same velocity as the grit. It provides a way to correlate the behavior of grit to a common design point. So if the clean sand particle, which is shown on the left, settles quickly, as is seen by the long black arrow, but the same size grit particle settles slowly, we can normalize based on settling velocity back to a clean sand particle. So the grit particle, because it settles more slowly, settles at the same rate as a smaller clean sand particle. Then the grit system can be designed to capture the smaller clean sand particle, and it will target the slowly settling grit based on settling velocity. This chart shows grit distributions from across the country where the physical size is shown in relation to the settling velocity, or sand equivalent size. Size distribution is shown across the x-axis, and SES, or settling velocity distribution, is shown across the y-axis. The black line represents the clean sand line. So a 400 micron sphere of silica sand would be expected to settle like a 400 micron sphere of silica sand, but the grit particles settle very differently. Almost all of the grit particles settle more slowly than the 200 micron clean sand particle, as they are shown below the line. That 200 micron clean sand particle is the conventional design point for grit systems, and based on this data, the conventional design point would miss most of the grit based on settling velocity. Some particles in the 250 micron size range would be captured, along with some very large particles in a couple locations, but most of the grit would be missed. You'll note that the size and settling velocity lines converge at about 100 micron, somewhere in the range of 75 to 125 micron. Based on this data, 100 micron is a good design point, as most grit particles are above the red line, which means they settle more quickly than a sphere of silica sand 100 micron, and they would be captured. A grit system designed to capture particles that settle like 100 micron sand would capture all the material above the red line. There would be some small particles, smaller than 100 micron, that would be missed, and also some very large particles from one location. As it is expected to be and has proven to be very effective, we'll reference this 100 micron design point as we go through the comparative data. With reference to the vertical slot sampling and testing methodology, Hampton Roads Sanitation District found the method to be consistent, repeatable, and effective. They considered the testing to be accurate as the results corroborated with system performance and the plant operating history. By using this common, repeatable test methodology, a comparison of the performance of the various technologies can be made, and it provides an unbiased performance comparison. The last note refers to grit settling velocity for the system. The performance comparison data that you're about to see is based on physical size alone, not settling velocity. But settling velocity is very important, as you saw in the last slide, and we will come back to the settling velocity later in the presentation. This is a list of the most common grit removal technologies, and they're the 5 technologies that we will compare. The top 3 were operating at Hampton Roads Sanitation District's treatment plants. The last 2 technologies were pilot tested as a part of the evaluation for the Army-based treatment plant upgrade. Hampton Roads Sanitation District found that their plant with the aerated grit basin had a large collection system with very little grit making it to the plant during testing, which was performed during dry weather. Fortunately, Columbus, Georgia had tested their aerated grit basin using the same testing method, and they were kind enough to allow us to include their data for this comparison. We'll move through the technologies in the order that you see listed here. First up is the detritus tank. It is an old technology to be sure, but there are still many in operation in the United States. A detritus tank is a large, square, shallow settling basin with a circular scraper to move the grit to a common collection point. It's sized based on surface overflow rate, and performance varies by design, but they're typically designed to remove grit 150 micron and larger. The Hampton Roads Sanitation District James River Treatment Plant had a detritus tank. They tested over 3 days in June in 2007. The units were running at 66% of their design capacity, and they collected the highest percentage of grit in the largest size range with lower removal efficiency as the particles get smaller. You'll see that as a consistent theme across all of the technologies. The detritus tank removed 66 to 73% of all grit larger than 150 micron, which is its design point. So it wasn't hugely effective, but it wasn't also a terrible removal result. But keep in mind, it was also operating below its rated capacity. Overall removal of all grit 106 micron and larger was 57 to 67%. The next technology to review is the aerated grit basin. Aerated grit basins are long, sloped bottom, rectangular tanks with flow moving the length of the basin. Diffusers are placed near the bottom along one side of the basin. Air is introduced via the diffusers to create a rolling or spiral motion perpendicular to the flow path. The heavier particles settle to the bottom while the air keeps the lighter organics in suspension. These are sized based on detention time, and performance varies by the design, but they're typically designed to remove 212 micron and larger, that conventional design point for grit. Columbus, Georgia tested their aerated grit basin in 2008 using the same test methodology as was used by Hampton Road Sanitation District. They tested for 3 days, and as we saw with the detritus tank, the aerated grit collected the highest percentage of the largest material with lower removal efficiency as the particle size gets smaller. On the first and third day, the aerated grit basin was operated at 66% of its design flow, and removal rates of all grit 106 micron and larger was 53 to 67%. Not significantly different than the detritus tank when it was operated at 66% of its design flow. But you can see the results on the second day were dramatically reduced. This was because they had a rain event on the second day, and during that day, flow increased by 35 to 75% above average flow rate. The flow rate increase represented less than a 2-time hydraulic peaking factor. With the higher flow through the system, it operated with a higher surface overflow rate, and resulting grit removal dropped from greater than 50% all the way down to 32% of all grit 100 micron and larger. As would be expected, when the flow increased, so did the incoming grit volume. The influent grit quantity increased from 28 pounds of fixed solids per million gallons to 74 pounds of fixed solids per million gallons. It was more than 2.5 times the average grit volume. A less than 2-time hydraulic peaking factor increased the grit volume by more than 2.5 times, and 32% removal of this higher grit volume would not protect the plant from grit deposition and abrasive wear. The final 3 technologies are all Vortex technologies. So let's take a second here to understand Vortex Flow. Vortex Flow has been used to separate liquids and solids for about 60 years. The design benefits include minimizing short circuiting, extending the particle residence time, and sweeping the solids to a central location for collection. When centrifugal forces are high, the separation can occur in a very small footprint. But in order to do that, the centrifugal velocities are high because it takes energy or head loss to drive that centrifugal velocity. As the head loss decreases, the centrifugal energy decreases, and device footprint has to get larger to accomplish the same separation. As the centrifugal velocity gets near or even below the force of gravity, the design benefits are reduced, and ultimately gravity governs the separation. The Vortex Grid systems that are used in the Headworks are typically low energy vortexes or forced vortex units. Low energy or low head loss units are needed to fit into a gravity flow hydraulic profile that you find at the front end of a plant. So these units typically have a head loss of around 1 foot or less. As the head loss is low, there's not much force driving the centrifugal velocity, so it is also low and can be less than the force of gravity. When gravitational force exceeds centrifugal force, then gravity is the predominant force field. Performance increases as flow decreases because surface overflow rate decreases as flow decreases, allowing the system to capture more particles. Very much in line with basic sedimentation engineering principles. So the third technology, the first Vortex technology, is the mechanically induced vortex technology. Hampton Road Sanitation District tested mechanically induced vortex units at 2 of their treatment plants. As mentioned, this is a forced vortex or low energy unit. Flow enters a circular chamber via a sloped ramp and feeds tangentially into the basin. The liquid rotates in the basin and exits above the inlet channel. A paddle is used to create what's called a toroidal flow path to assist with sweeping solids to a central point for collection. The paddle is needed as the centrifugal forces are low, and therefore the benefit of sweeping solids to the center for collection need this assistance. Sizing for this technology is typically based on manufacturer's standard designs, and typical performance is 95% removal of 300 micron particles and larger, with lower removal rates as the particles get smaller. The Chesapeake Elizabeth plant was processing 26 to 36% of the rated capacity in their Vortex units during testing. Again, we see this unit collected the highest percentage of the largest material with lower removal efficiency as the particle size gets smaller. You can see that the removal rate measured was well below typical claimed performance, which is shown on the second line, even though the unit was running at only about a third of its design capacity. Overall removal of all grit 106 micron and larger was 45 to 50%. A mechanically induced vortex unit was also tested at the Virginia Initiative plant. Again, the removal rate is highest for the largest material and decreases as the particle size gets smaller. This unit was operating near the design capacity, yet measured removal rate was still well below the typical claim performance. And overall removal of all grit 106 micron and larger ranged from 43 to 44%. The next technology was one of the two technologies Hampton Roads Sanitation District pilot tested for consideration in the Army-based treatment plant upgrade. The stacked tray system, or as HRSD referenced it in one of their papers, the gravity settling unit, is also a forced vortex or low energy unit. The stacked tray system utilizes a set of conically shaped polyethylene trays stacked one on top of another. The flow is then split evenly between the trays. By splitting the flow between the trays, the surface overflow rate for each tray is low, which improves capture efficiency. Sizing is based on surface overflow rate and the desired cut point particle. These units can be designed for 95% removal of all grit 75 micron and larger, but are more commonly sized for 95% removal of all grit 106 micron and larger. As the stacked tray unit was a pilot unit, it was operated at its design capacity. Again, we see higher removal rates for the largest particles and slightly lower removal as the particles get smaller, although it's not as steep of a drop-off as we saw with the other technologies. Overall removal of all grit 106 micron and larger was high, ranging from 88 to 89%. And the final technology to review here is the stacked tray unit. This was the other technology that was pilot tested. It was operated near its design, the final technology is a structured flow vortex. This too is low energy vortex. The structured flow unit has internal components to structure the flow and create a very specific flow path, allowing the flow to pass through while the grit is retained in the unit until it has adequate time to settle and be captured. These units are sized based on a volumetric loading rate and are typically designed to remove 95% of all grit 106 micron and larger. The structured flow unit was tested at flows ranging from 66 to 100% of design. Again, similar to the other technologies in that the removal rate of the largest particles is the highest, but also not as dramatic of a drop-off in removal of the smaller particles. Overall removal of all grit 106 micron and larger was 87 to 92%, with the higher removal rate observed at the lower flow rate. When we compare all the technologies, we see that the detritus tank removed 57 to 68% of all grit 100 micron and larger when it was running at 66% of design capacity. The aerated grit basin removed about 67% of all grit 106 micron and larger when it was operating at 66% of design capacity, but removal dropped all the way down to 32% when flows increased during the wet weather day and the aerated grit was running at its design flow. Had the detritus tank seen its full design flow, removal rates would be expected to drop, similar to what happened with the aerated grit basin. A higher flow rate means a higher surface overflow rate, which results in lower capture efficiency. The mechanically induced vortex units removed about 43 to 50% of all grit 100 micron and larger at flows ranging from 26 to 98% of design. The removal rate did improve as the flow decreased, although not as dramatically as was seen with the aerated grit basin. The stacked tray system removed 89 to 90% of all grit 100 micron and larger when running at design, and the structured flow unit removed 87 to 93% of all grit 106 micron and larger. Hampton Road Sanitation District found the testing to be consistent, which produced repeatable and accurate results. The findings corroborated with plant operating history and experience. Again, they considered the test methodology to be accurate. All systems saw reduced efficiencies as flow rate increased, indicating that gravity is the prevailing force field and sedimentation engineering principles apply. The aerated grit basin and mechanically induced vortex units had the worst removal rates. The stacked tray and structured flow units had the best removal rates, with removal rates 20 to 55% higher than the other technologies. That's a significant improvement over the conventional technologies. As I've noted with reference to the Columbus data, grit quantities increased significantly due to the effect of wet weather. The less than 2-time hydraulic peaking factor resulted in a solids peaking factor of over 2.5 times, indicating that the grit system should be effectively removing grit during those wet weather events in order to target a large portion of the grit coming into the plant. And finally, the comment here again with reference to grit settling velocity should be considered for the design. When settling particles, the settling velocity is obviously an important criteria. As mentioned at the beginning of this presentation, the current trend is to put a higher value on grit removal. The changes started around the time that Hampton Road Sanitation District began their grit journey. As a part of this new focus on grit, since about 2007, WEF, or the Water Environment Federation, assembled a grit task force, and both industry design manuals have updated their chapters on grit. Both design manuals discuss targeting smaller particles and that the conventional 212 micron design point does not protect plants from grit abrasion and deposition. Metcalf and Eddy even discusses the importance of considering settling velocity or sand equivalent size. In 2017, WEF's Grit Task Force published guidelines on grit sampling and characterization methods. The purpose of the publication was to review currently used grit sampling and characterization methods. One of those methods was the vertical slot sampler method that we've discussed here today. While the publication does not recommend any single sampling method, it does offer some insight into grit characteristics, stating that grit chambers, including vortex chambers, use gravity settling to remove grit from wastewater, and grit particles in sewage behave or settle like discrete particles. Therefore, the settling velocity of incoming grit particles, rather than their size, provides the best criteria for system design. The efficiency of the system can be calculated much more accurately when the settling velocity of the grit particles is understood. Settling velocity of grit is impacted by its size, shape, specific gravity, as well as the velocity and mixing energy in the channel. A grit settler or grit collection device should be sized such that the surface overflow rate is smaller than the settling velocity of the target grit particle expected to be removed. This chart provides the physical size as well as the settling velocity distribution of grit in the raw water coming into the Army-based treatment plant. The percentages shown are percent passing, a particular sieve size. If we focus on the conventional design point of 200 micron or 212 micron and physical size, which is the dark gray line, the grit at this plant is fairly large, with only 22.4% of grit smaller than 200 micron, which means that 70% of the influent grit is larger than 200 micron. So based on physical size data, the conventional design point would be expected to target a large percentage of influent grit. But the settling velocity numbers are quite different. About 50% of the incoming grit settles as though it's larger than 200 micron, with 50% settling as though it is a smaller particle. Based on settling velocity, the conventional design point would be expected to remove approximately half of the incoming grit. 50% removal is in line with the removal rates observed for the first 3 technologies we reviewed. Those systems were designed based on the conventional design point of 212 micron, and removal rates ranged from 32 to 68%. But by sizing the grit system to target a smaller particle, the 106 micron size that I've referred to through these comparisons, the grit removal efficiency improves to greater than 95%, regardless of whether we're talking about physical size or settling velocity. A 106 micron design point would virtually double the expected grit capture rate and allow very little grit to pass the headworks and into the plant. When designing the new grit system for the Army-based treatment plant, 50% removal was not adequate. The goal was to eliminate abrasive wear, the reduced operating volumes, and the increased maintenance and repair costs that Hampton Roads Sanitation District had seen at their other plants. If grit's not managed in the headworks, it's managed throughout the rest of the plant. It takes up volume in process tanks, reduces treatment volume and treatment efficiency, increases basin velocity. Grit accelerates wear on all mechanical equipment downstream, such as screws, mixers, pumps, and sludge dewatering equipment. In aeration basins, grit can bury diffusers, which then require additional horsepower to achieve proper treatment. In digesters, grit accumulations can lead to poor mixing, foaming, low volatile solids destruction, reduced gas production, as well as other issues. These issues can lead to increased labor and increased maintenance and operating costs. When designing the upgrade for the Army-based treatment plant, the design was to incorporate biological nutrient removal and would include a new headworks. Hampton Roads Sanitation District chose the stack tray unit for their grit removal system. They installed 2 12-foot 12-tray head cell units to process a total of 49.5 mgd and remove 95% of all grit 105 micron and larger. The system was started in 2015 and performance tested in 2016 using the same vertical slot sampler method. The results were excellent. The head cells removed 98 and 95% of all grit 105 micron and larger. This is a summary of the papers written by Hampton Roads Sanitation District covering their grit investigation. All have been presented at WebTech. The first 2 include the evaluation of the various technologies. The material from those 2 papers was compiled into the last paper, the relative performance of grit removal devices, which included the comparative data you saw here today. Following the original technology evaluations, and because the mechanically induced vortex technologies that were tested performed poorly, Hampton Roads Sanitation District put together a team to understand why and attempt to develop design modifications to improve the performance of those units. They developed 10 different baffle designs that were modeled and tested. That investigation became another paper, which was also presented at WebTech in 2012, How to Baffle a Vortex. The evaluation of the mechanically induced vortex technologies included CFD modeling as well as field testing. They found that the CFD model matched field data and could be used for their investigation. The mechanically induced vortex units had hydraulic short circuiting and collection efficiency decreased with increasing flow. Again, higher flow, higher surface overflow rate, lower removal efficiency. The technology was fairly efficient at capturing very large particles, larger than 400 micron, but it was inefficient at capturing particles smaller than 300 micron. They also found that the vortex motion was not the principal component for grit removal. The principal component was particle settling velocity, and therefore surface overflow rate is the key design criteria. The grit impeller or paddle did not impact grit removal, and of the 10 baffle designs investigated, only 1 showed improved collection, and that improvement was minimal. So when designing a grit removal system, it's recommended to know your grit. Consider performing a grit characterization that includes both size distribution and settling velocity. Unfortunately, a grit characterization is not as easy as taking a couple of grab samples. The influent must be sampled over a period of time in order to capture a representative sample and even just to capture enough material to process. A particle size distribution is a relatively easy standard method, but settling velocity is more complicated and more time-consuming to determine. In lieu of a characterization, regional grit gradation data can be used, and I'll talk more about that in a minute. Type 1 discrete particle settling velocity is the primary component for grit removal devices, and therefore surface overflow rate is the key design criteria for grit removal efficiency. The system should be designed for effective grit removal during peak flow and peak grit load, as we could see from the data in Columbus when during their higher grit volume coming in, their removal efficiency dropped significantly. And finally, select a grit removal technology which yields the highest value based on the treatment plant sophistication. A lagoon plant is much more tolerant of grit than a membrane plant or a plant that's designed to provide advanced biological nutrient removal. I mentioned the regional gradation data. Hydro has assembled what we call our North American grit gradation data sets. They're available for several regions across the USA and Canada and for several individual states and provinces. If you're interested in gradation data for your region, just let me know. We're happy to share the information. The data sets all include both physical size as well as settling velocity. So this presentation focused mainly on the grit collection component of the grit removal system, but when designing to capture a high percentage of incoming grit, it's important to carry that design requirement through the entire grit removal process. Thank you for your participation. I hope you found the information presented to be useful.